In this demonstration, we're going to specifically cover the element of components within the iris master analysis. We're going to go into more details about components, which are the various sections and fields that can be defined for a component within its component data tab, and how components can be added and indeed copied, how copies can be made of already existing components to quickly build up the number of components directly within the software. So new components can be added specifically within the master analysis, within process units and stations, units, plant areas that have been created, as was described in the previous exercise. Units with with administrator level rights can add new components within the given unit, and then they can start modifying its identifying information. The system this component belongs to the type of component it is according to KKS level 2. Bear in mind that already when a new component is created, the user selects one of the standard equipment / component types. Now, these equipment or component types do not have such a key impact on any kind of automation of the methodology or what kind of calculations are performed within the EN 16991 ESCOM RBI methodology, but the type of equipment is crucial when performing assessments within the API methodology. And in any case, of course, you as the users will want to correctly identify this component. Obviously, if it's of the type header manifold or valve, or if it's a heat exchanger, shell, or tubes, and so on. The next important point about components, and we will go through all of the fields in turn. The story with the KKS. This is a German power station codification and classification system, which was developed by the VGB, or the Association of Large Boiler Owners or Operators. It stands for Kraftwerk Kennzeichensystem, so power station codification system. This is something that has been accepted within ESCOM, and as we were informed, all of your components within SAP are classified with KKS. Some of the older stations have AKZ classification, which is another German acronym standing for Anlage Kennzeichensystem, Anlage standing for plant, so plant codification system. But I guess going on in the future, and especially within this tool, we are going to use the KKS to standardize basically the type of systems that components can belong to. And this is something that has already been implemented here. So when you do searching and comparison, or when you're looking at similar systems across your entire fleet, you should be able to, by going to, for example, high pressure superheating or feed water piping or pumping, to more or less get to the same kinds of components regardless of the station, regardless of if it is an AKZ or KKS station. Okay, how to add a component. This is something that we will demonstrate very quickly within the tool directly. Basically, you would go into your desired unit, and you would just add a new component of one of the set predefined types within this unit, and you would be presented with a brand new component with this comp ID at this moment actually being now automatically determined by the software. Previously, the users would have to make this kind of comp ID, which was something done at the very beginning of the project to make something completely unique. As was mentioned earlier, even the descriptive names of components, as well as the functional location codes, which were the AKZ or KKS codes, were not always completely unique, even within boiler plant area or single plant areas and units. we'll get into more detail about that. The standard component types, as was already mentioned, we've got some different icons that we've developed, and some are still under development for the different types of components. And initially, when Iris was primarily a software which dealt with API 581 and with that semi-quantitative methodology for the petrochemical side, of course, there were standard types of equipment which were defined, and certain ways of calculation, certain methods of calculation were applied depending also on the equipment type. Certain damage mechanisms were selected also depending on the equipment type and the range of design parameters of the component, the material, and the operating ranges. In our case, we use it also to clearly basically discern between the different types of components, and we've also included the second level KKS breakdown from the ESCOM adapted KKS book, where you have basically your second level, which is telling you what kind of equipment we're talking about. So you will see this very much when you get to your KKS codes. If you have LAB, feed water piping, for example, and then you have a number, and then you would have something BR. BR would be the piping. Or if it was a heat exchanger, it would be an AC, a valve, AA, and so on. Component basic data. This was already covered a little bit in the previous exercise, but we are going to cover it again in more detail. So again, we have our functional location code and basically the identification of the component, where it is within the system, and so on. And it should be easily identifiable and absolutely unique. The component ID, as I mentioned, was included because even the functional location codes were either incomplete for all components, or in many cases are the same. If we look at boiler tubing, you don't have each individual tube or even panel having its own individual code. So something needed to be made to uniquely differentiate all of the components there. And in many cases from the data gathering, the codes were either missing or were incomplete. The logic behind KKS and AKZ, of course, being that through a single alphanumeric combination, you should be able to pinpoint your equipment within a plant, within a unit, even within a certain system, even what kind of equipment it is, and all the way down to the component level, if everything is there and if you so require. The basic component and identification data, which will be demonstrated within Iris for each and every component, would be the data which identifies it within the correct system, the correct plant area, the correct units, and the correct power station. So we would have the comp ID of our component, to which process unit, as was termed generically, it belongs, or basically to which plant area, unit, and power station it belongs, to which system it belongs according to the KKS classification. What is basically its equipment level designation, also according to KKS. The standardized component type, as you will see in the demonstration, from which can be selected. Then we have our descriptive name, our description, which is relevant to us humans, if I can put it that way, unless of course you know your codes, and a lot of you do. The service start date, functional location code, be it AKZ, KKS, or Trigram, and yes, the status, a small extra piece of information which is saying whether it's operational, non-operational, whether this component has been scrapped, or testing, which is just a special little flag. If you want to make some kind of test component and test some parameters out, then you can set it as a testing component. As was said, the KKS, the reason to introduce it was Essentially, when we started comparing the information across the different systems, across the different, or let's say the same systems across the different stations, when we started getting more of the scorecards back, we saw that there was a lot of station-specific colloquial terminology, which was essentially, when we analyzed the KKS codes, at least for the KKS stations, was referring more or less to one and the same thing. And having all of these different colloquial terms for different systems at the different sites would make it rather difficult in the future to do any kind of meaningful comparison, or whatever we want to develop in the future as well as the things which are developed at this moment. So it really, there needed to be one standardized system, or one standardized classification across at least the entire coal-fired fleet, to make, for example, comparison of systems possible. And of course, since all of the components within SAP are treated with KKS, the logical way forward would have been to assign KKS system designations to all the components, including the ones at the AKZ stations. At the KKS stations, this was a simple task, basically just looking at the functional location codes of the component, whereas at the AKZ systems, we have had a lot of assistance from Eskom's KKS specialists to also translate these codes. And as an important side note, and a document which Eskom possesses and which everyone should have a look at, it is a document called, I believe, GG0806, which is an old Eskom document which is talking about the correlation between the AKZ and KKS systems. Very useful document, and will also be uploaded if needed with this tool, maybe on the organization level, to give users a guidance if they need it. So without further ado, maybe we can get to the demonstration, which is kind of tied to this exercise, which you will be expected to carry out. So we're going to go, we've already prepared a Letabo Unit 3 boiler and copied some components in the past. We're gonna start putting in some additional new components just to increase this number of components or equipment. And we're going to put in this new component / equipment and show you what happens where the software automatically defines the comp ID now, and how the basic information, the locating information for the component can be defined. So if we go to the software, I'm going to navigate to the master analysis, which is the second tab on the side pane. I'm going to expand that and go to Letabo Power Station. And I'm going to go to Unit 3, which I have pre-prepared in the past, and I prepared a Unit 3 boiler. Unit 3 boiler already has some pre-prepared components. In order to show you this, as you can see at this moment, and as was covered in the previous exercise, we do not have any component counts within the different stations within the entire organization or within the different units. So I'm going to go ahead and say show component counts. And in this case, if I expand Letabo, and yes, you can see if I expand Unit 3, you can see that I have actually 3 components there, these 3 components belonging to the boiler. So I'm going to go ahead and navigate to Letabo Unit 3 boiler. And now maybe go into some of these things in more detail, but first I want to show you these 3 boiler drums. Basically, what I did here and what I will show you now is I took one component, I'll show you now in the next exercise. I took one component, made it. It can be made all the way to the end with all of its design and operating data, and then you can essentially copy this component and make copies of it. This is something that can be very useful if you have a lot of similar components with a small number of differences, maybe in design or operating parameters, like large numbers of the same piping or similar vessels. You can just make the one component when you're collecting your data, finish it to the end, and then just make copies of this component. And This will be something that will be demonstrated. Right now, if I'm showing the component name, if we look at this pop-up window, we can show basically the comp ID, which we've developed earlier. We can show the proper functional location code, or we can show the description. At the moment, we're showing the descriptive name. I'm just going to go ahead and maybe show the comp ID so you can get more of a feel. And if I save this, you'll see it pop up in the tree here. You can see that actually I first went ahead and made this component, then I made a copy, and then actually I made a copy of this second component. If I go to one of these components, if I click on it, it's going to open the component basic information in the main work area. I'm going to go ahead and add an additional new component, but for the moment I just like to show you this and maybe cut away quickly from this unit 3 and indeed to another unit which has a much larger number of components to just demonstrate this feature here at the top, which is basically filtering and showing the components within the KKS structure based on the KKS systems which are defined for the components. But back to that in a minute. Just to quickly go through it. So this component has its comp ID. Here at the top, also here in the basic data. So the basic data is where one would edit all of this locational information or identifying information for this component. It is defined to which parents it belongs. It basically belongs to the boiler plant area of Unit 3 of Letabo Power Station. The admin level user can actually modify this and reset the component into some other unit if they so require. The KKS system, we have included approximately 1,700 KKS codes for all of the codes from the level 1 and level 2 breakdowns from the ESCOM adapted KKS book. And you can put this component into the various systems. This supports a like search. So you can search by the KKS code, and if you're not sure about the KKS code, but you are sure more or less of what kind of system it belongs to, if we say feed, and we start getting everything that has the term feed in it, if you want feed water piping or feed water pumping, or as I said, if this was, in my case, a drum, the drum would belong to the evaporation system, so HAD. So I can either search for HAD if I know the KKS code of the evaporator system, or if I don't know, I can say evaporator. Okay, we get a whole bunch of other evaporation systems in some auxiliary and ancillary systems, but for our boiler components, HAD is the right one to choose. The level 2, as I said, this is the equipment level. The ones which will be of most interest for the RBI assessment will be the A's and the B's. This is the mechanical equipment and the other plant mechanical equipment as well. So typically pressure vessels and similar equipment will be coded as a BB. Typically headers and piping and drains and so on will be coded as BR, piping duct channel. All of the valves should be coded as AA. Valves, you can get heat exchangers coded as AC, and then some other heaters, coolers, and so on can be coded as AH, and so on. Ejectors or attemperators usually coded as BN. Bear in mind that there is some difference even between stations. An example, I believe in most cases headers, manifolds are coded as BR, but I believe at Matimba Power Station I have noticed that headers are classified as BZ, special unit. So again, I guess that very much comes down to when the station was being commissioned and constructed, how it was coded. So you cannot expect absolute uniformity there. The component type. And this is something that I will show you when I add a completely new component now, but even once you've defined that, you can of course redefine your component type as something else if you've decided that it needs to be redefined. We have basically air coolers, temperators, uh, boiler components which belong to the boiler area, maybe tubes and so on. We've decided to keep the different types of compressors. So far, we've only seen compressors defined as compressors and pumps defined as pumps. Here, a little bit more difference is provided. So if you can select the correct type of compressor or pump, that would be much appreciated. We have filters and strainers, uh, fin fan coolers, uh, fired heater components, which are again components belonging to the boiler, furnace components belonging to the boiler. In addition, we've added a number of components to be aligned, so you do not need to use all of these components. For instance, we've added the components type tubing for all of your boiler tubing. We've added the component type header manifold to potentially differentiate your headers manifolds from your piping in some way if you feel the need to do that. We've added a heat exchanger water box. You have the shell and the tube bundle. And then we've added this heater cooler ACU because a lot of components were showing up with the second level identification of AH. And within the KKS book, it is heater cooler air conditioning unit. So it has been added. So for now, we go we remain with the pressure vessel, which is there. The functional location code, again, of course, from your equipment, from SAP or from the design or inspection or other documents where you will be able to get this code, you should be able to find it and put it in here. It's basically a text input field, so we would say maybe I don't know how the coding would go at Letabo, which is an AKZ station, but if it were KKS, 30 HAD, let's say 10, BB 001. Your standard colloquial description, according to the terminology of the site, you can write as long as you want here. You shouldn't write it too long. The service start date, what kind of component is it? Is it operational, non-operational? Has it been scrapped? When we say scrapped, then typically another component which is exactly the same as it would have replaced it, or is it a test component? Now, this brings us to this. These are the dimensional this is the dimensional information of the component, and as we saw within the analysis settings, we can select and change the length unit from millimeters to meters. We can select and change the volume unit from meters cubed to liters, and we can change the design pressure and the operating pressure from bars gauge to kilopascals. In fact, I'm going to go and do that now. So, yes, let's say 15,000 millimeters here, and let's say the inside volume of this. Well, actually, it can automatically calculate the volume for you. Again, as a cylinder, just as you would do on the data gathering sheet. So if you were to put in something that is 15 meters long and, I don't know, say 1,500 millimeters across with a design wall thickness of a matter of 55 millimeters, and you go ahead and save this component, it is actually going to calculate a total inside volume based on a cylinder. And you can then go ahead and overwrite this. Obviously, if you have some more accurate information, whatever you input here is going to overwrite the automatically calculated value there. Now, just to demonstrate this, maybe I just go to design pressure and say something like 237 bar as the design pressure, or maybe a little bit less, 210 bar, and the operating pressure 189, temperature around 350 degrees, or yes, 350 degrees, operating at 330. Sorry, I just need to save this component again. And then demonstrate the change of the dimensions. Or the presentation of the dimensions, if I may say correctly. So now we've saved the temperatures and pressures that we've input. If I go back to analysis settings, and bear in mind, if this is the master analysis, it's any subset that any user opens, any one user that makes the changes here, it will be visible in the whole set. So the master analysis, the reason why it's called the master analysis is because it also kind of acts as an analysis, but it is not. It is all of your most current information, which is uploaded into one big kind of like analysis, but in that sense, it's similar to individual analyses, but actually it is supposed to be the master repository of your most current information. So here, I'm not going to change the length unit. It's in millimeters, and ESCOM uses millimeters. I'm not going to change the volume unit, but I am going to change the pressure unit to kilopascals to keep in line with everything that is being used. I'm going to go ahead and save those analysis settings. It only does it extremely quickly. And if I go back to the component, you should see now that our pressure units have been changed and it's been converted correctly. So 210 bar, 21,000 kilopascals gauge. So it's always taking the gauge values, the ranges of these. I'm just going to go quickly over the allowable ranges for input. For pressures, basically at the very base, the software takes bars, but it's very straightforward to convert to kilopascals, and the input range both for the design and the operating pressure is from -1 to 3,000 bars, or in this case, -100 kilopascals to what, 3 million kilopascals, or 300. So if you set it at 0, that is atmospheric pressure. The design temperature and the operating temperature, I believe, goes from -273, which is something you will never ever experience, to about 2,000 or 3,000 degrees again, which is again something that your stations will never ever really see. But the point is that you've got the possibility to input the range that you need. The next field that we have here, material field, and you can put in your textual material designation according to whichever standard or code was used for the design and the fabrication of this equipment. And you also have the material group, and this is something that is extremely important for the API side, but is also very useful to have with the ESCOM RBI. Regardless, because you can, the more components you have correctly classified with the material groups, you can start to make use of the material type search criterion within search and compare, and also within when you start adding components in analyses. So 10 chromo 910 would typically be, again, 2 1/4 chrome, 1 moly steel. X20 and similar materials would be 12 chrome steels. And so on. I think that there is that interesting material which is used in medium temperature or high temperature feed water applications. It would be carbon half moly steel, the 15 nickel, copper, molybdenum, and so on. So this is not a mandatory input, but it pays if you have a metallurgist with you. It pays to correctly group or classify the material, and then simply have this correct information for future quality of the information. The next field that we have is basically the pressure testing field. The way this operates, if this is ticked off, all of the information is lost in these fields. So if it's not subject to pressure testing, you do not need any of this information, obviously. However, if it is subject to pressure testing, it's going to automatically determine the test pressure, assuming you don't input anything there, as 1.25 times design pressure. You can, of course, overwrite this and input your own value. It's assuming you haven't put in anything for the test interval, it's going to automatically take the test interval from the analysis settings for this process unit, for this Letabo Unit 3 boiler, whatever was set there. If, for example, 72 months was set there, it's going to take the 72 months. If you override it and put your own value, it's going to override this. And you have the chance here to input your previous test date. So if I go ahead and save this component now that I've ticked off subject to pressure testing, it should bring 1.25 times 21,000 kilopascals down there. And assuming I've put in an interval, which I have, it's going to put in 1.25 times design, and it's also going to put in the test interval from whatever I've defined on the higher level. Prescribed inspections, something that is used for API, but can also be used here, of course. Your inspections as prescribed by law, your intervals as prescribed by law. Internal inspection every 36 months, external inspection maybe even every 12 months. Not exactly sure, and then the efficiency more tied to 581. What would be the interval and when was the previous inspection performed? Something that can be input but does not have to be input and was not part of the previously of the RBI scorecard or the data gathering sheet. Other data, basically data sources. Does the system to which the component belongs or to which the component is attached contain safety and protection devices such as safety valves and so on? Yes or no? Is there online monitoring functionality within this system? Can you get any kind of computer trends and so on? Yes or no? Is there previous inspection information available? If yes, you can cite the inspection data sources here. Is there previous failure or repair history? If yes, you can cite the failure or repair data sources here. So basically Part C data sources, design data, Part D data sources, operating data, Part E data sources if available, IMT data, and Part F data sources, repair or failure data. SANS data, extremely important for the ESCOM RBI methodology. What you basically do is select your equipment as one of the standardized PER or SANS or PED essentially equipment types. Your equipment can be broadly classified as a pressure vessel, piping, or a steam generator. So this, let's say if it was a boiler drum, it would be a steam generator according to PER and also PED. It would belong to the assembly of the steam generator. Your operating fluid, you would select it and input it here. So it would be water, steam, two-phase in this case. All of this stuff is automatically calculated based on SANS. It automatically goes into the right chart based on the type of equipment according to PER/PED and SANS 347 and the operating fluid. This is a hazardous fluid. If it is a steam generator or a pressure vessel, you need the volume. If it is piping, you need the diameter, and I believe even the tooltips here, which have been requested and which have been implemented with a lot of formatting, should make it clear. You input both the nominal diameter. If your equipment type or component type is piping, you input it into the diameter field. If your equipment or component is a pressure vessel or a steam generator, you again input the internal diameter in the diameter field, and this is explained in the tooltip. So for the piping, please use the nominal diameter, treat valves as pipes, and so on. For pressure vessels, also steam generators, well, actually for steam generators, you are going to use, if you treat the entire boiler, you're going to use the volume of the entire boiler, basically from the pressure test certificates, and which is something that I'm going to go ahead and input now. So typically for these very large boilers, it's going to be around the 80 to 90,000 liter range. So I'm going to put 88, well, maybe 90,000 liters, which would be the content from the economizer inlet to the main steam stop valves, the full content when it is pressure tested. And if having this and okay, having the not sure what kind of steel, I suppose carbon steel, maybe some other more special kind of steel for the drum, maybe not. If I save the component, it should now automatically calculate the SANS for this component. So if I go ahead and save, and here we go. It has automatically looked up for this type of PR, PED, or SANS 347 equipment and the combination of the fluid. What is the applicable figure? Is it a dangerous fluid? Yes, it is treated as a dangerous fluid. What are the states of contents of this kind of fluid at atmospheric conditions? It's basically going to flash into steam or be a gas. And looking at the pressure times volume product, it's going to basically put it into category 4. Another very specific thing which has been provided is the possibility to override the calculated SANS. And I believe here in the tooltip, it also comes with an important warning. You may use this. What has been experienced before is sometimes there was insufficient information to even do the basic SANS categorization, and there were other instances which were also pointed out by the end users that, of course, according to PED and PER, assemblies like steam generators should be treated in such a way that all elements belonging to the assembly, all the different components or equipment, tubes, whatever belonging to the boiler, should take on the hazard category of, or the highest hazard category within the assembly. So if this boiler or the steam generator is a category 4, essentially all of the boiler tubing, all of the equipment or components which are going to be inside this assembly are going to assume the highest design hazard category of the assembly. And the tooltip here gives a note and says, please only use it in the following situations. And if you choose to use this override, please you have the comments field and you need to minute or comment why you have used an override from the calculation. So you should use it, again, if you have a number of components treated as an assembly, and one of those components or some of those components have a higher design hazard category compared to the rest, then the other ones need to assume the design hazard category of the highest hazard category ones. And if you've looked in all sources and you're missing some key information to carry out the design hazard category classification, in this case, if you can make an educated guess, you can go ahead and override. I'm going to now just override to show you quickly what happens. So if I select a 3 here, it's going to highlight it red. Basically, I'm overriding whatever it's calculated with my input. Or I can just flick back and now it's looking back at the calculated. So once you override this and save it, it's basically going to take this overridden value. The damage mechanisms, we're going to cover them in more detail within the analyses because you can add different damage mechanisms in different analyses, of course, and analyze your component for different damage mechanisms. The most important point, it's basically a selection on level 1. You can only select one, the one most dominant, most likely to occur, most susceptible damage mechanism. Once you get to your level 2, you have a checkbox selection and you can select multiple damage mechanisms. There is a guideline for the different damage mechanisms that should be selected for components in different areas of the boiler, turbine, and Genelec plant, the generic failure frequency guideline, a good guideline that is being developed and constantly updated. Please make use of that guideline. It's also going to be attached with this tool, but primarily on Hyperwave, where you can then look to add the correct kind of damage mechanisms that are expected for the correct types of components, and also to ensure that consistency of your results. So to get to the demonstration, I'm going to try and add quickly a new type of component, and then I'm going to try and maybe modify some parameters of this component and just quickly show you how I can copy it into multiple copies of additional components. So I'm going to say here I can add a new component, and I'm adding a new component for the Letabo Unit 3 boiler, obviously the unit for which I have opened. Let's say I'm going to add, because I already have these drums here, let me try and add some piping. So I just need to find the piping. Here we have piping. I'm going to add a piping type component. The screen is going to refresh. It's basically going to save that information in the database, and your new component should show up in the tree on the side. And you can see that this component has automatically been received a comp ID, and this is something that has been done. It takes basically the first letter of the component, the power station. It takes the next two consonants. It takes the unit. It takes the plant area, B for boiler, T for turbine, G for Genelec, and C for common plant. And then it takes something which is called the component ID within the database, which is completely unique for every single component in there. Once you start making copies, then the CID may not follow the completely unique CID anymore within the database, but at the moment when this component is created, this is the unique ID of that component within the database. So you can change this to whatever you need or leave it as such. It's already been placed, of course, within boiler, Letabo Unit 3. Let's say I want feed water piping, and let's say I don't know what feed water piping, what the code of feed water piping is, so I'm going to go feed and see what I get. Okay, I get the feed water system LA. I get the feed water piping system. There it is, LAB. I have the information I need. I put it into a system. I said it's piping, so I'm going to look for BR in my case, piping duct channel, or even if I didn't know that, I could just say piping, or just PP. In this case, it brings the piping duct channel. If I knew the functional location code, I would put it. I'm just going to invent one here. So I don't know what the terminology it is that ESCOM uses. I believe it. First, you have the unit in the front, and then you would say LAB maybe 10 BR 001 and main feed water piping to economizer. Yeah, let's keep it as operational. Diameter, let's say 250 millimeters. We don't need the length for the piping, nor has ESCOM been inputting the length. Design wall thickness, I'm not exactly sure what would be the design wall thickness of such piping, but quite high pressure. So let's, well, at this moment, without looking at the information, the material might be that 15 Ni Cu molybdenum niobium. I don't remember. It's 564 or something like that. And this is a carbon half moly steel, but it's made specifically for these kinds of applications. For feed water piping at elevated temperatures, boilers, and so on. Design temperature, let's say around 300 degrees. Let's say the operating temperature is 250 degrees, and the design pressure would be very high here. So again, 210 bar, and maybe operating at sorry, kilopascals. Kilopascals, 21,000, because I've set it into kilopascals and operating at 19,000. And we would say, for example, it is subject to pressure testing. It's going to automatically bring back something to me, and it's going to automatically bring back the interval. Again, as I said, we can say, yes, it has safety and protection devices. Yes, it has online monitoring. Yes, it has information history. And again, this depends. I mean, depending on the data sources that you have. So let's say there are some C schedules and documents and so on that you have here. Again, operating trends, documents, data that you have here, and so on. You would put that in. We're going to classify it as piping according to PER, PED, and SANS, and we're going to say that it is water well above boiling temperature. And we are going to save this component and see what we get. Probably it would even be an insulated pipe, but yes. And an important note, actually this is going to be something of more interest once you get into the analyses, but it's already telling you that yes, it needs to be done. Currently it's on level none because no RBI or of any kind has been performed on this brand new component which we've made, this feed water piping for unit 3, but it already says that yes, the next level of assessment does need to be done. And how does it check this on level 1? Well, it checks if the SANS hazard category is category 1, 2, 3, or 4. In case it is any of those, then it would say that yes, level 1 assessment is required. So it has, yes, automatically placed it into hazard category 3. It has the calculated SANS. We have all the information required to categorize it as such. So we could even keep it that way, unless it was, yes, maybe the piping. Or, this one doesn't get. If it gets pressure tested, if it's treated as part of the steam generator assembly, which I believe it isn't, then it could even go to a category 4. But we keep it at category 3 for now. And now, I would just like to show you. Maybe I don't have such a large number of components, but how you can display these components. And this is all very handy when you have very few components here. Once you start getting very large numbers of components, I've now saved this, so I will quickly go out of my Letabo Unit 3 and show you Letabo Unit 4, which is the proper unit which was analyzed properly. So if I go to the master, go to Letabo Unit 4, and take the boiler, take the turbine. Let's take the turbine for a change. Go into the turbine. You're going to have about 1,000 components here, maybe even more, and it's one big flat list, and it's even with component IDs, making it even more confusing to look at the start. But with the whole KKS implementation, what we have done is allowed you to filter these components basically by the units. These components belong to, well, in this case, 834 components belong to Letabo Unit 4 turbine. You can filter them by types. So you can say we have this much piping, this many valves, and then all the components are grouped underneath their types. But surely the most interesting way, in fact, let me just quickly demonstrate this by types. So we have other equipment, heat exchangers, pressure accessories. But when we say other equipment, we mean yes, all of this piping here and some other types of components. These should actually be within the vessels. But if we go to KKS, which is the most interesting one, all of these components are properly set within their right KKS systems, which are defined for them. So we have steam, water, gas cycle, 400 components there, and 435 components belonging to the main machine set. If we go to steam, water, gas cycle, we have feed water system. We can expand that, and then we get our feed water tank, deaerating tank, feed water piping, feed water pumping, and so on. If we go to feed water piping, we get our 92 components, the different pipes and valves which belong to the feed water piping system on the turbine side. If we want to look at something related to the turbines, we can open the main machine set. MA, main steam turbine plant, you have high pressure, intermediate, low pressure turbine. So if we want to look at high pressure turbine, then we have all the components which were defined as belonging to the high pressure turbine, and so on. So this is a very, very useful way to break down very large numbers of components according to a standardized breakdown. And something that can be shown, but not so effectively within this unit 3, because obviously we have only 4 components there at the moment. So just to quickly end off this exercise, we've now created the component. Here it is, defined according to KKS, and we have the drum in its 2 copies within conventional heat generation, H, pressure part system HA, evaporation system HAD. If I expand that, I've got 3 drums which will all put into HAD. And we have our piping within feed water piping, LA feed water system, feed water piping system. There is our component. Once you have components defined as such, and say for example, especially in feed water piping or some places where you can have a lot of, let's say, relatively similar components, the diameters may change and the wall thicknesses may change, but the components may be roughly similar in material of construction, in the pressures and the temperatures at which they're operating. What you can do to quickly build up the number of components. Now I have this component, I've defined much of what I wanted to define for it. I can just right click on this component and say copy as new component. It's basically going to make a copy of this component with all of its information into a new component. And when we get to actually assessing, and I've on purpose left out the assessment information at this point, because if you have this component with some of its level 1 or level 2 assessment information, it's actually going to, in that copy, also copy all of the assessment information as well. So if you just want to create your component data, then you can copy your blank components and assess them later. These are actually being left blank for a reason, because in one of the following exercises we would like to demonstrate the automatic factor suggestion which has been implemented. So I'm going to go ahead and copy this component once, twice, maybe 3 times, and you can see what happens there. Since my original component was already set in LAB, of course it's copying all of the parameters of this component and making a copy. I can now change the name of this, the descriptive name of this component. I can even keep this copy if you so wish. You can change your functional location code, your dimensions, wall thicknesses, and so on. If this was like a 40% or 60% bypass or some other smaller pipe, which wasn't the main feed water pipe. And I can make as many copies of this component as I need. Copy as new component, and it just copies it. So this has been, well, a kind of a medium detail level look into how to add new components within the master analysis, how the different data fields and areas for these components, how you can input these data, how you can change the display within the analysis settings of the dimensional information, pressure information, or indeed the component, which name is being shown in the tree, the descriptive name, or the functional location code, or the comp ID. How it does the SANS calculation, that you can override the SANS. Be very, very careful, only in extreme circumstances should you override the SANS, and how you can make a lot of copies of a single component once you have the basic information that you want.